My name is Spyros Kondilatos and I'm going to present our paper on the generalization of representation uncertainty in Earth observation. Recent advances in computer vision have introduced pre-trained uncertainties. Similar to representation learning, these uncertainties are learned in the representation space of deep learning models trained on large-scale upstream datasets, enabling zero-shot uncertainty transfer to downstream tasks. A method that scales well and provides generalizable uncertainty estimates is loss prediction. This method introduces an uncertainty head implemented as a multi-layer perceptron on top of pre-trained frozen representations. This module is trained to predict the upstream task loss as a proxy for aleatoric uncertainty. Representation learning has shown great potential in Earth observation, allowing learning representations that transfer zero-shot to improve downstream task performance. However, the concept of representation uncertainty remains unexplored. In this work, we try to answer, does representation uncertainty hold promise for Earth observation? To answer that, we investigate whether and under what conditions we can provide uncertainty representations that can generalize effectively zero-shot to diverse Earth observation applications. Despite our work is focused on Earth observation, we make some additional contributions that hold promise for broader computer vision tasks. First, we expand the current approach to multi-label and segmentation tasks. Then we make an initial effort for spatial uncertainty estimation, and finally we assess the practical utility of representation uncertainty by comparing their alignment with task-specific uncertainty proxies. Before starting our analysis, we first define the factors that may affect the uncertainty generalization in Earth observation. First, we have ground sampling distance. Ground sampling distance influences the level of spatial detail affecting object detectability, textures, and patterns. Second is domain of interest that influences the objects that can be found in Earth observation images. For example, marine environments exhibit distinct patterns and objects compared to terrestrial scenes. Then we have the granularity of targets. The required semantic detail varies across Earth observation tasks, ranging from fine-grained knowledge of small-scale objects, like tree species classification, to high-level patterns like forest detection. And finally, we have the spatial arrangement. Object positioning can reveal very important insights into the processing shaping an Earth observation scene. We use the following investigation pipeline. We train supervised classification models on large-scale Earth observation datasets and then freeze their representations. The uncertainty module is then trained on top to predict the loss as a measure of uncertainty. Then, the generalization of the representation uncertainties is evaluated across various previously unseen downstream datasets, taking into account the variations in the semantic factors. For evaluating the uncertainties, we use two complementary strategies. First, we evaluate them directly in the representation space. This is done using a novel set of metrics that expand the evaluation to multi-label and segmentation tasks, following the principle that representations with lower uncertainty should be accurate, while inaccurate representations should exhibit higher uncertainty. More information about these metrics can be found in our paper. Second, we evaluate the uncertainty in downstream tasks. We do so by assessing their ability to provide reliable uncertainty estimation for downstream applications. This is done by training supervised classification models on downstream tasks and measuring the alignment between their losses and the zero-shot uncertainty estimates. The main insights of our work can be summarized as follows. EO pre-training yields reliable uncertainty estimates, while pre-training on optical data does not generalize to Earth observation. Then, aligning the resolution between pre-training and inference is essential for gaining optimal generalization. Pre-trained uncertainties have the capacity to identify noisy data. Finally, our pre-trained uncertainty is shown to be reliable for zero-shot uncertainty estimations. You can find more about our work using the following links. Thank you.